Okay, I think we talked about the nature problem of multicollinearity last week. Okay, so I'm going to use one of the example which show in the textbook. Okay, but at the same time, I do have some PowerPoint, and you may also look at the PowerPoint. Then let's talk about this. All right, and this is the data set. Okay, we just download it using the CONS8. Okay, you may not have it. Rachel, you may share with Steve. Okay, and download this eViews CONS8. Okay, then I'll show you how to do in eViews. Okay, all right. I also have the data of eViews. Where is it? Where is it? Okay. eViews. You know, if you have the data set, is using Excel, okay, and you may just drag all the Excel file into the eViews, then automatically convert it to the eViews file. Okay, I think this is some similar idea of different data packages, okay, that they can share their data set. Okay, all right. And let's see the where is my, okay, how? Okay, actually this is, if you turn on the file, okay, open the file, then the data set look like this, okay, and the C here means constant, okay, so it automatically has this two variables. One is constant, the other one is residual, RESID. So whenever you run the regressions, then the residuals will automatically store in the RESID variables, which is the updated. Okay, so you run, several regression models. The last one, residuals, will be shown on this variable. Okay, and the rest of the variable is the one we are going to use. Okay, so in this example, CO. Okay, if we look at the textbook, okay, let me open this textbook and see the definition. All right, this is in our textbook on page 247, and this is one of the example, okay, with data. And CO means the annual consumption expenditures of the students on items other than tuition and room and board. Okay, so except the tuition and also room and board, the rest of the additional expenditures which it stores in this CO, the definition. Okay, and how do you think the students' expenditures from? Okay, there's two variables. One is called YD, the other one is called LA. YD is the annual disposal income. So maybe the annual disposal income, maybe also this money is from parents. Okay, their daily expense allowance or something. Okay, so this is called annual disposal income. And the second one will be LA. LA is called liquid assets. It's from the savings, for example. Okay, And it means that the assets can be immediately changed to cash. Okay, so with these two sources, will decide how much money, how many the students can expend. Okay, so how do you think these two variables? I mean the regressors, x variables. In other words, now CO is our y variables, then LA and YD will be x variables. How do you think these two x variables, one source, of course this data is like hypothetical data. Okay, so the authors use this data since it is hypothetical, means that they really do something about the data. And if you have the disposable income, the relationship between the disposable income and the liquid assets, okay, must be pretty close. Okay, if we wanted to see the numbers, okay, the numbers of these two variables, we can do like this. Okay, I'll show all these three variables since the variable in this data set is not big. It's only 7 observations. So I'll show all of them. Okay, you can highlight the variables. So the first one is Y and ID using the control key. Okay, then you can open this as a group. So automatically you can see the numbers inside. Okay, so you can see the LA and YD is pretty similar, right? Right, as the YD goes up, LA goes up. Okay, so LA and YD are what we call regressors, and which is the main topic of chapter 8. When we talk about multicollinearity, is talking about the relationship of x variables instead of with y. So it's x variable itself among x variables. So multicollinearity problems is nothing related to y variables, but only among x variables. So we don't want to, we have x variables with highly correlations. If we have the highly correlation among the x variables, then it causes multicollinearity problems, because these two variables, the role of individual x variable plays in the regression analysis is confounding. Just it's mingled together. It's hard to differentiate their own individual role in the regression analysis. Okay? So actually, we know that LA and YD are pretty close. So in terms of the nature of the problem about multicollinearity, if these two variables are highly correlated, then it causes problem. So in this situation, now I already showed in the whiteboard last week that since one of the variable can be, write it in terms of the other variable. But actually, this is not perfect multicollinearity. It's just imperfect, but it's highly correlated. Okay, although I cannot totally replace one with another, but this two is really mingled together. It's really confusing. Okay, so we can show that if I put all these two variables as regressors at the same time in the regression model, how it works. What does the output look like? Okay, so this is today what we wanted to say, the consequence of the multicollinearities. Okay, all right. So how do we use the e-views? We already these two master students already know how to do it, but not the PhDs. Okay, so let me. Okay, let me show you how to do it. Okay, the quickest way is choose the y variable first. Use the control key and following x variable. Okay. So this one was YD LA. Okay, I'm using the sequence as our textbook. Then hit the right keys. Then open as an equation. Do you see that? The second, choose the as an equation. Okay? Then you will see the pictures like this. This is the pictures, okay? Then we're using ordinary least squares methods, which is the first one. If you turn on this one, there's a lot of methods which we are going to cover, some of them this semester. Okay, the first one is using ordinary least squares. We haven't talked about any other ways except OLS. So we're still using OLS. Okay, this is a default. Okay, then it shows that I have y variables following two x variables and the c is the constant. Okay, then I'll hit it. Confirm, okay, then this is the output of EViews. So what did you see from here? If we want to explain the output of regressions, so this is the hypothesis testing. So you understand it. Where is J? Oh, she's not feeling well. Okay. Okay, this one. What did you see from the output? What did you find out? You know how to read this output, right? Okay, we have two variables. One is YD, the other one is LA. According to this output, the probabilities, the last column is the p-value. Okay, how does this p-value tell us? Is too high, right? Actually, our alpha level is no more than 10%, right? So all of them is higher than 10%. Okay, even we're using one-sided test or two-sided test. We know that all the p-values from output is two-sided. Then if we wanted to use the one-sided test, we have to divide the p-value from the output. But actually, if we are divided, it's still higher than 10%. Okay? So it means what? The p-value is too high means what? Reject? Is it reject? Do not reject. Remember that, at the beginning when I teach the hypothesis testing, I used to tell my undergraduate students that whatever the conclusion, is from the hypothesis testing, just, really counters, the difference from what your intuition. So do the opposite side, then you will get the correct answer. But not now, okay? We need to know the exactly reason. Actually, we wanted to test whether, I'm working with the two-sided. I'm not thinking about whether it's positive. Actually, this is positive relationship, right? If you have more money, then you get more consumptions, right? So, okay, let me just also use so this is beta 1. Beta 1 is a coefficient of YD, and actually is greater than 0. So now hypothesis will be less than and equal to 0. So if the p-value is greater than alpha, means this, we have no we have not enough evidence to infer this one alternative hypothesis is correct, is true, right? So in other words, is do not reject the null hypothesis. Right? Means this variable, although we are thinking that, oh, maybe this is very important variables, but actually it turned out, the result turned out to be not significant. Yeah, that's the reason. This is all the consequence of multicollinearity. Okay? Okay, so I'm showing this example to show all the consequences. Okay? So this is do not reject the null hypothesis. Therefore, one of the consequence, okay, let's see. If you have textbook, okay, maybe I have the PowerPoint too. Okay, let me show you the PowerPoint. Okay. Any consequence, okay? Consequence. Okay, let's see the consequence. The consequence of multicollinearity, okay, you can see this from textbook too. The first one's estimates will remain unbiased. What do we mean by this one? Means what we estimate, whatever the coefficient, whatever the standard error, okay, is unbiased. You know, unbiased, this word is really from statistical terms. Means that it's robust. You know, unbiased means just correct. You can thinking about that. But it's not the correct, the true coefficient. But you know, it's when we say unbiased means the expected value of the estimator is equal to the populations. Okay, that means unbiased. So the unbiased means that the OLS methods is correct. Okay, so multicollinearity problem doesn't affect. We're using OLS estimator. This is what we mean. Okay, okay. The second one, the variances and standard errors of the estimate will increase. We'll refer to this one later on. Okay, and okay, the third one. The computed t-score will fall since this one is increased. The second one says this one will increase. You know, I need to use the one example to do the comparison. Then you will know why it is increased. But here, you just accept the truth that the second conclusion is this one standard error. Standard error means the output. I mean, the output we have it. Standard error means this one, okay? This one is increase, okay? And so the t value will be decreased. This is what the number 3 say. The computed t-score will fall, okay? Then number 4. Also, estimates will become sensitive to changes in specification. I mean, the estimate means the coefficient, also the standard error. This is sensitive to this change in specification. Means if you have add more variables, or if you change the sample size. Now I have just only 7. If I increase it 700, all the estimates changes a lot. So sensitive to the change in specification. And look at this one, number 5. The overall fit of equation and estimation of the coefficient of non-multicollinearity variables will be largely unaffected. This is what Steve just said, that how come the adjusted R square is so high? The adjusted R square high means what? model fit well. Now, adjusted R, what's the meaning of adjusted R square? Steve, do you know that? Still remember that? Yeah, the higher of the adjusted alpha square, the higher, the better the model fit. Okay, so if you look at adjusted R square is higher, and the model fits so well, how come our X variables is not significant? Is this sort of counter how to say that? Counter effect, right? They're complicated. Okay, therefore, this is all the consequences you can directly see from the output. Okay, so let's go back to our output. Okay, and you see that all the important X variables is not significant. And if you look at the model, this is what I say. Adjusted R squared is so high is 83.5%. And look at the F statistic. This is talking about the model. Okay, the model F statistic and the model's probability is 0.012. Which is significant, means the model fit well. Okay, this whole model. When we say whole model, this is for individual. When we say whole model in this example, we are working with beta 1 equal to beta 2 equal to 0. This is the null hypothesis. An alternative hypothesis will be at least 1 beta j not equal to 0, j equal to 1 and 2. This is the whole model. This is individual. This can be 1 or can be 2. Okay, we have 2, right? Okay, this is for individual. And you're using t-test. And for the whole models, you are using f-test. And actually, the f-test tells us that significant. And the t-test that none of them is significant, since these two are all, pretty high p-value. Okay, so in other words, now I know that there are problems with multicollinearity. Now what do you do? If you know this multicollinearities, what do? You may like to try to ignore one of them and just use either one of them. Okay, so you also run the regression of, just only one variables. So you need to run 2 simple regressions. One with LA as a regressor, the other one use YD as a regressor, just separately, okay? So let's run 2 simple linear regression. Do I have this too? And that's right. This one. Oh, excuse me. Did I do that? Let me go back to. Excuse me. Go back to my. How come I didn't save all of them? Equation. I use this one. So this one will be by equation 1. Okay, save it. Then I'll do individually. Now I'm using these 3 equations. Show these 2 equations at the same time. Okay. Okay, this one. And also equation 1. Okay. All right. Let's see what we have. I'll put this one. How to put them? And it looks better. Okay. You all have these 3 models. One is with 2 variables, we just saw it. And on my right-hand side is each just individual one. Okay. So let's see the individual one. Look at YD. The one with YD as a variables. Is that significant? It is, right? The p-value is small. And look at the adjusted R square. With YD, the adjusted R square is still 86%. With these 2 variables is 83.5. So 1 variable is even better. Okay? And this one is using LA. Let me show the result. It's higher. Okay? This is 86. And the LA is also significant. And look at the direction. Although this was 2 variables, I mean the expected sign is positive. Okay, all of them are positive, and these 2 are also positive. Okay, the sign doesn't change. Okay, and follow our expectation. So this is the pretty typical example with multicollinearity problems. Means individual, if you get out of one of the multicollinearity variables, then individually they play their own role to the affection to the y, to the effect to the y. Okay? All right? And look at the standard error. Let's look at standard error. The second points of the consequence means the standard error will increase, right? Let's see whether it is increased. Look at the standard error for YD for both variables is 1.03. And just if you have just YD itself, it turned out to be 0.15157. So it's almost 3 times higher if you put YD and LA together, right? So the standard error increase, okay? And the coefficient is different too, right? Look at the coefficient with YD itself and with LA both, okay? The coefficient with YD itself increase, just double. But the standard error reduce 1/7. Okay? So in other words, that will affect the T statistics because the T is using coefficient divided by standard error. Okay, so standard errors in the denominator, which is reduced a lot and reduce more than the coefficient increase. Okay, therefore, the T statistics, look at the T statistics, is really several times of the original with two variables, therefore affect the probabilities, p-values, to be smaller until the significant. Okay, and we all know that if we have, since this is all the estimation, so the explanation of this coefficient will be very important, like for example, the YD. YD, if you have more disposable income in this situation, means $1 disposable income will affect almost $1 of consumption. You know, look at the 0.97 means you have one more disposable income. The consumption will be 97 cents, so almost 1-to-1. Okay, and this one say that if you have $1 liquid assets, you will spend your consumptions like 8 cents or 9 cents. But whatever, if I have only LA as a variables, the adjusted R square is as high as 86%, and the same as the YD. But you put them together, the adjusted R square decrease because their similarities, their highly correlation problems caused the OLS estimation, confusing. All right? So if you go back to C to read the books for the consequence, okay, 8.2, section 8.2, there's 5 consequences, okay? Then I just show from the PowerPoint that this consequence, okay, will be like this. The estimates will remain unbiased. Second one, the variances and standard error of the estimates will increase. Third one, computed t-score decrease. The number 4, estimate will become sensitive to changes in specification. Means that I have 2 variables and also run the 1 variables. Okay, so this means I'll change the specification, then estimate will be sensitive because the estimate, when the estimate change sensitive means that they change a lot. Okay, either you change the specification or either you change the sample size. And this means that the estimate is not stable. I think we wanted to have the model with stable estimate. Means you use the correct methods to do the regression analysis. Okay, then I think the number 5 is also important too. If you have the variables which doesn't have, X variables doesn't have multicollinearity problems, no matter the the specification change or the sample size change, okay, the estimation will not be affected. I mean, in these examples, I do have 2, which is multicollinearity. But if you have another variable, the third variables, which is not correlated with this 2, then that variable's estimation will be very stable. Okay, we'll have that example using the other data set, which is CHA.1, which I already given to you. And that will be some part of our assignments. Okay? All right? Understand what I'm saying here? Is that clear? Okay? So this is what we say the consequence of multicollinearity. And there's one examples from our textbook, and there's no data set. So in that way, we need to look at the textbook, but I think I have the PowerPoint here. So let me show one part of the result. Okay. All right, this is an example. Okay, this is our second example without any data. Okay, let's just read it from this output. Okay, this is usually this is the regression. We have to write it down, and there's a parenthesis. Parenthesis is the standard error. Okay, then the lower one with the estimation coefficient standard error. Then following is the t values. Do you see that? So can you read this one? Okay, this is very small. I mean, some part of important information from the output. Okay, how many sample size do we have with this example? 50. Okay, we also show the adjusted R square. Okay, all right. So you know how to read this one. Okay, so look at the 8.13. Let's see the definition of all of these examples. Okay, the y variable PCON says is the petroleum consumption in the certain state in the United States. Okay, there's was some measurement units called trillions of BTU. I don't quite understand this one. Maybe, huh? Well, I think this all these engineering students know it, but I don't know that. But anyway, this is the measurement units of the petroleum. Okay, all right, and this is y variable, and we have 2 variables. One UHM is called urban highway miles within the state. I mean, how the urban highway miles means, what do you mean by that? The longer the highways, then the distance is far, maybe, then you'll drive it and you will consume more petroleum. So we're expecting the positive signs, okay, with UHM to the petroleum consumption. Okay, and the second one is tax. What do we mean by tax? Means the gasoline tax rate in the state. So the higher the tax rate, maybe, the less the consumption. Well, but sometimes it's not quite clear. If you need to, do that every day, no matter how far you live, then you still have to consume your, drive car, right? So it's kind of not quite clear, but maybe the effect of the tax rate will be the negative. Okay, all right. So maybe we can see the expectation is negative. And the third one is called motor vehicle registration. Means that if you have the motor vehicle, you need to have license, right? Driver's license, it's not driver's, a vehicle's license. Okay, so the more vehicles, motor vehicles, the more number of registration. So the more cars means more consumption of the petroleum. So we are expectable for positive signs too. Okay, so this is 8.13 is the output using 50 states in the United States. 50 states in the United States. Then what do you see from equation 8.13? Anybody want to say? Registration become negative. Okay, we expect positive, right? The more vehicle, more motor vehicles, more petroleum consumption. So the sign is different. Anything else? R squared is really high, means the model is okay, pretty good. You know, when we say the whole models using R squares, look at the alternative hypothesis, at least 1 beta not equal to 0. Means what? I have 3 variables. As long as I have at least the 1 variable is significant, then the model is fit. Either the other is not very significant, but never mind. We're not asking for all the significant X variables in our model. Okay, although it is not significant, but the literature say that that is important factors we have put in as the X variables. If it is not significant, it really doesn't matter. Still have to stay there. Okay? All right? So the model is good. Anything else? One thing we see the output here, if we have the output from the computers, we immediately see the p-value, right? And this is not from the computer's output. It's just the summary of the output. And it shows the t-value. In this case, we can use critical value approach. Using the critical value approach to say something about the hypothesis testing of these 3 variables. Alpha level, okay? Since we're working with the directions of the one-sided, let's use the alpha level is 5%. Okay? Then what's the critical value? You need to know the sample size 50. Then what's the degrees of freedom? We're using T distribution, right? So you're familiar with T distribution? No, okay. Hypothesis testing is using, did you see that we have T statistic when we see the output? Why it put as a T statistic? Because we're using T distribution. Okay? T distribution is pretty similar to standard normal distribution Z. Okay, they are, actually it's from the same family. But T distribution is different from standard normal distribution. T distribution is, we don't know the population standard deviation. But standard normal is with the knowledge of population standard deviation. Therefore, though there's a little bit different missing informations compared with the standard normal distribution, they invented to have a different called T distribution. Okay, let me show the T distribution. I think I have the table here. Excuse me, okay? Let me see. Yes, I do have this T distribution. Look at this one. This is how T distribution look like. This is really like standard normal distribution, right? And with the mean look at the middle parts is 0, 2. Okay? And the t distribution, we need to know the degrees of freedom. Okay? Then for regression analysis, how do we decide the degrees of freedom? You all remember? N. Wait, now N is 50, right? Then anything else we have to consider in order to know degrees of freedom? Minus 1. Just only 1? Yes, minus 1. The 1 is consequence. I mean the constant. And also minus the number of x variables. So how many number of x variables do we have? 3, right? So 50 minus 1 minus 3 equal to 46. Okay? So look at the degrees of freedom with 46. Let me show the tables. 46, okay? Here, 46. And this is called area in upper tail, means one-sided, right? Upper. So now we're using 5%. So with 46 degrees of freedom and 5%, so the critical value is 1.79. So what does that mean? Since, well, some of the variable expect negative, the other one is expect positive. 2 of them is positive. There's only one text variable is negative. So with the negative one, the critical variables, critical values will be the area in the lower tail. So means the negative sign. With the expectation of positive, this will be the positive sign. Okay, let me show the positive sign. The diagram maybe help you to understand it. If I say this is a t distribution with 46 degrees of freedom, so if I say this is 5%, okay, the critical value we just found out from the table is 1.679. Okay, so let's go back to see our output. Okay, I have the t values with 5.92, negative 2.77, and negative 1.43. Okay, let's see. Why don't we see this one first? Okay, this what means what? The correct sign. So the t value is 5.92. Where is it? Somewhere here, very small. The number is big, 5.92. And the p-value is the tail area of 592. So this is what we call p. This is alpha. This is alpha. So in this case, with this diagram, p is smaller than alpha, right? So in other words, using the critical value approach, just look at the t values. If this t values is greater than the critical value, then you can immediately know that p is smaller than alpha. Okay? All right? So look, follow expectation. We expect this is positive. This is positive. Okay? And this one is 9.82. I just 5.92, I'm sorry. And I just show it. We know that p is smaller than alpha. And what is the REG? the t-value is negative 1.70. So somewhere, this one is the middle is 0, right? So I have the negative one will be somewhere here. Negative 1.43. Always remember the p-value is the tail area. I mean the tail is the directions. Okay? The REG will expect positive. So the tail will be on our right-hand side. So although this one looks the tail is this one, but we should see all the right-hand side instead of left-hand side. So the look at the p-value, the whole area of this one means the p-value is much greater than alpha. So not significant. Understand what I'm saying here? Always look at the diagram. Also you have to follow your expectations. So the expectation for the sign of individual variables, the sign of the coefficient of individual variables is very important. Although the result is different from your expectation, I mean the sign, do not change, do not affect it by the result. Okay? Follow your expectations, because that is more important than the output. The output is using the data. That's the one is so means prior. Expectation is prior. Then the output result is ex post. Okay? So ex post is the result. But prior expectation is according to the theory, according to the literature, which is more important than the output. Okay? So in that case, this is not significant. Okay? And this is significant. We expected the negative sign, and which is negative 2.77. So in other words, if I look at the negative sign here, my 1.679 can be here, and this is 1.679, which is negative. And this one is alpha, 5%. And ours is negative 2.77. It's here. And now the tail area will be the left-hand side. So P is smaller than alpha. Okay? So UHM and TAX is all significant. But REG, the sign is different, and it is not significant. Okay, let's stop here for a while. We'll come back to this example. Okay?